I want to talk about machine learning routing protocol for wireless ad hoc networks. Before I get into this, I wanted to extend my thanks to Shweta, who has been very good about not only prompting me to do this, but setting all of this up and all the technical details. I literally couldn't have done it without you. So thank you very much for that. So if it's a good talk, you give credit for it. If it's a bad talk, you blame me. All right. So I'll outline for the talk. I wanted to first talk a little bit about wireless ad hoc networks, but you're all networking people, so I'm going to try to move through that quickly. Are there any AI machine learning folks here? Not a one. Okay, I can handle that. Not you. No. All right. Then I want to talk about learning algorithms, which is what's going to be, I think, of greater interest. Talk about previous work in routing protocols, both in terms of various things, including reinforcement learning-based routing protocols. Then I want to talk about a new cross-layer routing metric and introduce a routing protocol called WARP5. After that, I want to talk a little bit about machine learning, how that works in WARP5, and then the experiments and results that we've done with that, and this is in comparison to not only shortest route protocols, but the queue routing protocol as well. A few observations, and then future work. Now, there are going to be things that come up. You're going to have questions. That's great. I will handle some of them, hopefully just on the spot. I'm anticipating one or two questions that are going to have lengthy answers. And I've got something prepared for that if we've got time. So, just don't hesitate to ask questions. And I will do my best to take care of all of you. So what is a wireless ad hoc network? Tell me if there's anything anybody doesn't know. A collection of nodes without an infrastructure. They are exchanging information. They are doing some larger purpose, but the nodes themselves may start out not even knowing who their neighbors are. They have to self-organize into some sort of network. They communicate peer-to-peer, and they move information through intermediate nodes from source to destination. The nodes act as routers. They are handling the intermediate nodes, and the packets are sent by radio or infrared transmissions. Wireless routing protocols. Network throughput is increased by using low-power, short-range transmissions through intermediate nodes. The goal of the routing protocol, then, is to select the best sequence of intermediate nodes. So our question, then, is how is the best path defined? What criteria do we use to define the best path of intermediate nodes? And how do we find the best path of intermediate nodes? Valid questions to apply here is why even have intermediate nodes at all? Well, if you're communicating through wireless networks, wireless communication, inverse square uses a lot of power. Maybe you're in a situation where you don't have that power, you have a lot of small battery-powered nodes. You reduce network throughput if everybody just shouts at their intended destination node. You reduce the throughput to the throughput of the entire network, the throughput of one node communicating to another node. You actually you get more out of the network, get greater throughput by using intermediate nodes at lower levels, lower power levels. Let's see, other things to consider. The fastest wireless rate supports about 2.5 million bytes a second, assuming about 1,500 byte packets. This is 802.11g, 54 megabits per second. The fastest wired rate is around 10 gigabits. That's about 500 times faster than our fastest wireless access. So that underscores the importance of using the wireless ether as efficiently as possible. Various factors affecting wireless ad hoc networks. We have the contention for the communication channel. We have the environmental noise, which can corrupt packets. We have router congestion, just trying to move the packets through the routers, and of course the selection of intermediate nodes. I've got the outline. We're going to look at learning algorithms now. Learning algorithms. A learning algorithm can be defined as any algorithm whose performance, according to some obvious measured metric, improves with experience. A learning algorithm can actively try different actions whose effects are not initially known to gain experience to make better decisions about what to do in the future. we can extend this idea from active learning to passive learning, and say a learning algorithm can passively observe the effects of other things going on in the environment, including non-learning algorithms, again, to gain valuable experience to make better decisions in the future. The learning algorithm has to turn whatever it experiences into some sort of meaningful information. A lot of the AI folks have some very nice, very good algorithms, but they don't talk about, well, how do you take something that you perceive in the real world and how do you turn that into meaningful experience? There isn't a lot of discussion of it in the AI world. In the learning environment, what AI does provide is a lot of very convenient and very useful terminology. There's the idea of an agent that has some sort of explicit goal. The agent can take a number of finite actions. It has a finite set of actions available, and it's selecting which action to take. The agent perceives its environment to determine the state of the system. And again, the state of the system, there are a number of finite distinct states. There's a reward or a cost, which is a function of the state and the individual action chosen, that is the result of an individual action taken in the state. The agent ultimately wants to maximize the reward or minimize the cost in the long run. So we talk about problems of sequential control. Challenges to learning algorithms. The result of a lot of number crunching, a lot of these algorithms, is something that is evaluative but not instructive. Evaluative means it gives you a number, it's not making a decision. An example would be there's an X% probability that this link is broken. The estimated time to destination is Y, where X and Y are clearly numerical quantities. It is not providing instructive statements. It's not saying this link is broken or this is the best neighbor to use as a downstream neighbor. It is up to the agent to take the evaluated information, interpret that, and then make some sort of decision based on that information. Learning algorithms must balance exploration and exploitation. Exploitation means the algorithm is taking advantage of what it has already gained, if anything, to make a decision, to make the best decision it has so far. But because of changing conditions or possibly incomplete information, the algorithm must also explore in search of better alternatives. So you have to say, all right, how much of my effort am I going to devote to exploiting things and getting the job done? How much of my effort am I going to take to find a better one? And I'm trying to emphasize it. No one can see my hand gestures. I want to spend most of my time exploiting. I want to spend a small amount of time exploring. I need to balance smoothing and responsiveness. A lot of times input data is noisy in the statistical sense of the word. And I want to be able to sort of smooth out those little variations. That is smoothing, but then I also want to have some kind of responsiveness. If I have a noisy information and the situation changes, I want to be able to recognize that change in some reasonably short time frame. See, the biggest challenge for learning algorithm is it has to explore the state space and take a lot of exploration to convert to an efficient policy. A policy being defined as what the agent does in different states. And they're making a lot of stumbling around before the algorithm starts to even begin to focus on an effective policy. And what's worse is the environment may change faster than the algorithm can converge to an optimal policy. So our pertinent questions we want to address in this talk. What actions of learning can minimize router congestion? We want to lose as few packets as possible. We're going to get our data from source to destination to those intermediate nodes as quickly as possible. Second question, what actions of learning can mitigate data packet loss due to noise? We're in a noisy environment. There's a certain amount of inherent packet loss available. Would it be news to anybody here that says, there's that theoretical formula that says you only get zero noise at absolute zero? Anybody not know that? So if I wanted to have all my packets and never lose anything, I have to run it at absolute zero, so I suggest we all run a jacket. Oh, I'm going to stop that tense humor now. Okay. We got our outline. All right, previous work. I'm not going to read all of these what I want to emphasize is that the work in transmission rate selection has shown a gradual evolution from just sort of fixed things toward being increasingly adaptive at making decisions based on some sort of experience. Now, these algorithms were, as they evolved, were not written by AI people. These were actually written by networking folks who had no clue about AI, but they've shown, again, a kind of adaptive learning behavior and an increase in performance in so doing. Shortest path routing protocols, there's a lot of those. Let's see, what can we say about that? They also show some evolution. On-demand route construction as opposed to trying to provide, let's see, the network proactive communication had proven too costly, it was quadratic in the number of nodes. You know, if you have some routing protocol that's trying to be the link state protocol and say, all right, we're going to keep everybody informed of how to reach every other node all the time, because all the nodes are moving around. That just became too expensive. So a lot of evolution has moved toward on-demand route construction. Minimizing nodes involved in route discovery by reducing nodes involved in discovery or by proactively sharing routing in limited spheres within the network has also been some of the work done in shortest path routing protocols. There's also been another area with reinforcement learning-based routing protocols. Reinforcement learning is an AI term. This is for sequential control, where the agent is taking an action, getting a result back in some quantified fashion, and using that quantified information to make some sort of decision. If I'm not oversimplifying, that's the essence of what reinforcement learning is. One of my advisors, Michael Litton, some years ago had come up with an idea called queue routing, which is based on a queue learning, a generalized abstract queue learning algorithm. The queue routing is a protocol that, again, where each node just sort of randomly selects a neighbor, gets some idea back of the estimated time to the destination from that neighbor, and uses that information to select the next route, the appropriate neighbor. Let's see, what do? We treat the routing problem as a learning algorithm in sequential control. It's a Markov decision process. Is that a term to anyone here? Not that great. Each link level unicast gets a cost signal that is sent upstream to the MAC level sender. And that information contains a new estimate of the time to destination for that particular route. There are many interesting variations here over the years of this, all done by AI specialists. So we've had AI people playing with routing and who knew nothing about networking. We had earlier stuff where there was an AI influence that was being done by people who knew nothing about AI. So something interesting. Somebody had to come along and kind of mesh the two. Queue routing is based on queue learning algorithm, which I talked about for Markov decision processes. It is hoping to minimize an estimated time to destination for the data packets. Each node X learns some estimate Q of X for each destination D for neighbor Y. The node selects the downstream neighbor with the lowest Q value most of the time. It's doing that most of the time to do exploitation, but it's also exploring. By every once in a while, it will randomly choose a different neighbor to see if conditions have improved for other neighbors. The downstream neighbor always sends a feedback packet after every MAC level transmission based on the packet queuing time for each MAC level unicast. So for every MAC level data packet that goes this way, there is a feedback packet that goes in the opposite direction. It is learning an update formula that is an exponential weighted average. The limitations of queue routing. Like any queue learning algorithm, it needs lots and lots of data before it converges. And while it's converging, your data is moving around the network and it is not necessarily getting to its destination at all. The upstream feedback packet reduced bandwidth for data packets. If you have nodes that are communicating data and routing control packets all on the same channel, every packet you send this way, you're sending another packet this way. You just cut your bandwidth that's available in half. The upstream feedback does not count for the effects of noise. If packets are getting lost, this is not in the queue routing algorithm. It just does not deal with it. Queue routing was originally devised for wired network where packets really don't get lost. data packets sent on exploratory paths increase router congestion in high offered load situations. Even if you have two radios and you're just moving the data packets, the routing control packets on a separate channel, the data packets wandering around, add to the congestion problem and actually distort congestion feedback results that the algorithm is trying to use to learn.
If it needs lots of data before conversion to an optimal solution, then how does it deal well with drastic or pseudo-drastic changes to the environment? So like if a radio were to go now, all of a sudden, would it be able to react quickly to that, or?
It would not react quickly to that. It would attempt to communicate. In fact, what happens in a noise, let's back to your question and say, all right, if we have a slightly noisy environment, as the environment becomes noisier to the point that the link is just broken, we are now getting a slower and slower effect. One node A sends to node B. Maybe that packet gets lost because of noise. Maybe the feedback packet gets lost because of noise. If we increase the noise level so we're losing maybe half the packets, suddenly here's the packet, get the feedback, here's the packet, get the feedback. We're losing them, and that effect sort of slows down. So by the time we're losing 99% of the packets, the algorithm is only getting data at maybe 1% of its former rate. So the algorithm doesn't know that there's a lot of data getting lost. If it's monitoring the speed of these things, it's just sort of perceiving things much more slowly. So by the time you get to a complete link breakage, it just says, maybe it's trying another link and saying, oh, I'm getting better time through that. But if we break the link and it thinks, oh, we're getting a nice short routing time, forwarding time through this link, it'll just keep using the link. Sorry, summarizing the previous work. The work that had been done in transmission selection was limited to the link layer and does not affect which link to use, even though they were making decisions about which transmission rate to use. The prior assumption had been, we've already committed to using this link. They're not making a decision about which link to use. The shortest path routing protocols ignore noise. They're going to try to get the shortest path no matter what. They don't care how noisy the environment is. They either ignore noise, they ignore congestion, or they just break out right. And we can see an example later on from the experiments where one breaks in a peculiar and interesting fashion. The reinforcement learning-based protocols, they ignore noise and traffic variability. So what do we need from this? We need a cross-layer routing protocol that takes information from the different layers as needed, combines them, and considers noise and router congestion in making routing and forwarding decisions in multi-hop wireless ad hoc networks. I wanted to illustrate this with a simple congestion problem. We've got a tiny little network here, 6 nodes. The 2 nodes on the left here, 1 and 4, want to communicate with nodes 3 and 6. They can't do it directly. They have to do the intermediate nodes 2 and 5. We have a high offered load situation where the offered load is 80% of the router forwarding capacity. So on the routes that you see here, node number 2 cannot handle all of the traffic without losing some packets. Just in this one example, the router forwarding capacities happen to be homogeneous. They don't have to be, but in this case they are. Nothing in the previous work solves or prevents this congestion problem. If we had a shortest path network, a shortest path protocol is perfectly happy with the top picture. It's not going to even try to modify it. A queue routing protocol, node 2 is going to push back to node 1 and it's going to say, hey, I'm really congested here. And that pushback will be based on the total router load that node number 2 is experiencing. Similarly, node 4 is going to get that same pushback. It says, here, I'm really congested. Here's some feedback to that effect. What nodes 1 and 4 will do under queue routing is they'll simply both switch to node 5. So what we have is we've gone from the top picture to the bottom picture. We have not solved the problem, we've just shifted the problem. Node 5 at some point will respond the same way node 2 has, shift back to the top, and we just sort of alternate with queue routing between the 2 pictures.
If you have 8% offered loads, why are not doing a scheduling algorithm and you are doing queue algorithm?
Okay.
If you are so much overloaded, why don't you do a scheduling algorithm?
I did.
I mean, but you are You are trying to learn the environment and
Yes.
adapt yourself.
Yes.
Instead of that, like, why don't you just schedule?
He's just showing the slide as these are examples of the type of problems where if you don't throw on
Yep,
these
don't
extra
worry.
things, this is what you encounter. So yeah, he does do that essentially. It is. So these are like background.
All right, we're showing the background. All right, so why machine learning and networking? All right, we've established the shortest path routing protocols don't particularly do the job that we need to do. The pure reinforcement learning tends to stumble around a lot before it converges. I mean, we're talking, I've seen examples, 10,000 iterations, people lose 10,000 data packets. And that's in a relatively small, straightforward network. Congestion and noise conditions can change unpredictably, which is an ideal situation for machine learning. We cannot predict beforehand what we're going to need or where things should go. We have to deal dynamically with changing situations. And that's where some sort of machine learning and adaptive algorithm comes in. The combined approaches can use network condition information and deal with congestion and noise in wireless networks without loss of generality. So what I'm going to show you is something. I've got some examples, but they work in a more general sense as well. All right, cross-layer routing metric. We all know the protocol stack has multiple layers. What I'm doing is now taking information from different layers, combining them into a single metric, looking at noise and router congestion. So my contributions are a new time-based routing metric that uses recent experience for making routing decisions. So we're going to look at the effects of noise, we're going to look at the effects of router congestion, we're going to combine those into a single metric. Also contributing a new cross-layered wireless routing protocol, or 5, that uses the new routing metric and machine learning mechanisms to establish routes and adjust existing routes as needed in response to congestion or noise situations. So cross-layer routing metric. Noise affects unicast time and failure probability. Again, we're discussing as noise goes up, that probability of failure tends to go up. Introducing quantities, PF, probability of unicast failure, and the time to complete a unicast, TM. They are characterized by MAC layer information, and they can be learned. What the MAC layer tells us after each transmission, the transmission either fails or it succeeds, just 1 or 0. That information by itself, that this one has failed, this one has succeeded, is not useful information. That's a direct perception. We now have the idea of a learning algorithm that's going to take that and turn that information into something useful. We're going to turn that recent information as trend information and turn that into what is the probability of failure. We're going to look at the last several recent unicasts and say, what is the average transmission time? How long did it take us to do those multiple 802.11 transmissions to complete a unicast? Let's see, router congestion affects delivery time. The more packets are going into the router, the more congested the router becomes. Router congestion can be learned from the network layer, not the MAC layer. We can combine the routing metric into something we express as time. The 3 components of the formula. TM is just how long it takes, the first component is how long it takes to complete a single transmission. From initial transmission, including all of the 802.11 random backoffs, how long does it take until what is my average transmission completion time? Middle term, what if I'm losing some of these packets to noise? I take the probability of failure, plug it into the central term, multiply that times the time it takes to complete a unicast, and that adds to the time it takes. And the third one is how much time is spent in the router based on the router's forward capacity and the arrival rate at that router. Probability of failure and the time to complete a unicast are learned from the several recent unicast attempts. Again, we're sort of smoothing that information, averaging out, so we're dealing with variability of data. The arrival rate learned, again, from smooth recent observations, balancing that responsiveness and smoothing and saying, all right, we want something that reflects recent information, but not the single most recent data point. We want an average because our data is statistically variable. The forwarding capacity of routers is heterogeneous, so we plug this formula in even if we have routers with different forwarding capacities, the same formula still applies in the routing protocol. We're going to look at the WAR5 routing protocol now. Wireless Adaptive Routing Protocol version 5. It is a cross-layer on-demand protocol. It builds routes as needed. The routes are constructed using only local information. It considers noise and router congestion in route construction and forwarding decisions. The route selection is meant to minimize packet travel time between source and destination. It can also modify existing routes as needed in response to noise or congestion. Route construction, unlike the stumbling around approach of queue routing, it uses a more traditional approach where it sends broadcast request packets to the network, they propagate through the network. We will propagate them at most some k times as set by the system designer. Maybe we need to do the same propagation multiple times to account for noise. The destination intermediate node broadcast replies when we get to the destination, and the reply broadcast propagate backwards toward the source. The metric in the reply is the estimated time to destination based again on prior experience with routing, with congestion and noise. The propagating noise add their own cost to the time to destination before they propagate, so the time to destination increases through the nodes as they propagate back toward the source. The newer and cheaper time to destination estimates always propagate, which makes sense. If you have new information, even if your old information was fine, newer information is always better than older information, and within the same time frame, shorter information will get propagated ahead, where longer times will not get propagated. Nodes keep a time to destination for all neighbors. AODV, one of the shortest route protocols, seems to go to a lot of trouble to find ways to get rid of route information that seems valuable information, and I think it was a tremendous waste to throw that nice extra neighbor information away. Routing error messages are not needed in response to packet loss or noise in modifying the various paths through the network. Here is a nice route construction example. This is castle topology. We want to, this is poor artistry, I know, but I'm trying to create an example where I may be in an urban environment, where I've got a building there between, say, nodes 3 and 4, 9 and 10. I might have in some complex topology out in the real world where I've got a mountain there between the nodes. I need to be able to communicate from the nodes 1, 2, 3 on the right side over to nodes 4, 5, and 6 on the left side. In this case, I'm going to have a nice example. I'm going to build a route first from node 3 to node 4, as you see in the second picture. And with lack of any other information, WarpFire will just build the shortest path. That is the most efficient thing based on initial information. When node 3 and node 4 are established and I am in a high offered load situation, communicating between 3 and 4, I'm going to build another route, again, high offered load between 2 and 5. I build the second path. This path that's constructed is just a cheaper path, given the load on the pre-existing route. When I build a third route, 1 to 6, again, based on the high offered load taken up by the 2 routes, this third path just happens to be the nicest route, the fastest route, based on the previous experience and the previous 2 routes. So looking at how Warp 5 would respond to this, our original problem, again, in the top right, top left, it is ignored by the shortest path protocol. Queue routing just manages to flip between the top left and the top right. They don't resolve the congestion. They don't know what to do. They're still talking in terms of total router load. Warp 5 can prevent the problem at route construction by saying, oh yes, one of those routers, it is more expensive to go through there. I will find a shorter path, or we can adjust the routes. So we have 2 solutions. Either we just go 2 across, or 4 to 2 to 6, 1 to 5 to 3. They are equivalent solutions to the same routing problem. No questions so far? All right, machine learning, and how does Warp 5 learn? At the map level, it's learning about learning which transmission rate to select. The machine learning mechanism is called epsilon greedy. It is balancing exploration and exploitation. Epsilon is some small number in Warp 5 to 0.05, meaning 95% of the time it goes with the shortest neighbor, it goes with the fastest transmission rate in terms of total time. In a slightly noisy environment, a slower rate is more resilient to noise, and you will result in less transmission time. And it is that real transmission time that we're using to minimize it. So in a slightly noisy environment, we want a slightly more resilient rate, we want a slightly slower rate. Whichever one does it in the least time, that's chosen randomly most of the time, 95% of the time. The other 5% of the time, we try different, possibly faster rates to see, can we do a faster transmission rate and minimize the overall time because the noise conditions might be changing for us. The unicast failure probability. This is an exponential weighted average. We're taking those success or failure, that 1 or 0, yes or no, those extremes. We're averaging them over time to get something that's in between 1 and 0, with the probability it's going to fail. You know, I've sent one, it failed, I sent another one, it passed. Hey, I've got a 50% chance of unicast failure. I am turning recent percepts into meaningful probability information. So again, I'm taking what I perceive, turning it into something that I can use. Packet arrival rates, again, because of that variability, 802.11, that random exponential backoff, how quickly the packet's arriving at an individual node, that's going to vary a little bit. Again, that's statistical variability. We're using a sliding window to smooth that out, but if this window is fairly narrow, so if the rates change, you know, we see a significant change, we can respond to that. Root stabilization time, using expectation maximization algorithm, is making inferences from possibly incomplete or missing percepts. Not all the nodes see, when roots change, not all the nodes see a change, but they are still making their best guess based on expectation maximization, again from past experience, to figure out to get a good idea of how long it takes for it to change and stabilize in the network. We outline experiments and results. This is the fun stuff. All right, we did some experiments on congestion avoidance and noise avoidance. These experiments were run on.
What is expectation maximization?
Excuse me, this thing is humming a little bit.
The expectation maximization, how can you define that? Can you explain what is expectation maximization? EM. In your previous slide. What is EM? Can you explain that?
Not readily. I would have to refer you to my dissertation, and there was a chapter in there. It's chapter 5.
Sure.
5.4.
Okay. That's fine.
Okay. I'm sorry.
No problem.
Okay. All right. The simulator it's an event-driven simulator. It emulates 802.11 MAC protocols. Links are 1 hop radius. Communication range is, in these things, always very Cartesian, 1 up, 1 down, 1 to the left, 1 to the right. Avoiding router congestion. The communication radius is 10 meters. Nodes were 9 meters apart. The nodes have an identical routing queue size and forward capacity. The nodes here are heterogeneous. They didn't have to be, but it's just easier to do this. I discover routes in the 3 to 4, 2 to 5, 1 to 6 order, like we had seen in the previous example. The nodes are single and dual radio, so we did 2 sets of experiments where we do all of the control information and the data packets on one channel, and then we do another set of experiments where data moves on one channel and the control packets move on a different channel. High offered load was 2/3 of the routing capacity of each node. So, and the route discoveries were initiated 4 seconds apart. So this is our topology again, just to reinforce that idea. I gotta stop saying reinforcement learning thing. Avoiding router congestion. The top 2 pictures are AODD, a shortest path routing protocol. When we did it with 2 radios, all right, before we go any further, the combined offered load by 3 nodes is about 100 packets per second. So if we want to imagine a line running across there, across here, that would be what we're shooting for. AODD with 2 radios actually did not perform as well as AODD with 1 radio because the control packets moved independently of the congested routers. They just always chose the shortest path for nodes 15, 16, and 17, and we got, it's a little noisy, but it's 50 packets per second. AODD with 1 radio actually did better. It stumbled around after the first 2 routes, and it kept trying and trying to establish that 3rd route, and it took it almost a minute to do it. And when it did, it established a route that avoided these nodes because these nodes were so congested with data and control packets they became essentially invisible during the third route discovery. So which led us to this topology. Queue routing had this effect. I had two exploration rates. At a very low rate of 0.01, one packet and 100% on some exploratory direction, and a high exploratory rate where one packet in 10 was sent exploring. The difference between 1 and 2 radios was not significant. Turns out the low exploration rate, when it had an ID, got better throughput. With the higher exploration rate, I got lower throughput. What was happening was I had a lot of wandering data packets that were just sort of being sent in random directions, and they were clogging up the network. So what was surprising was 1 or 2 radios didn't make a difference. I got about the same level of congestion and wandering data packets whether I used one radio or 2. So it was the exploration rate that was more interesting than moving a lot of control packets around. Queue routing uses a lot of control packets. We good so far? Okay. All right. This is the same picture of queue routing as before. The topology is interesting because it's using all the links all the time, moving packets. That's why every error was used there. Warp 5, again, we were saying we wanted a rate of about 100 packets per second. Warp 5 caught on. It said based on past experience, it solved the problem, got those packets moving very quickly at an optimal rate, given the high offered load for each of the routes involved. We have avoiding router congestion, some summarizing statements here. Queue routing never found stable routes. It was always exploring. Some of the routes were better, but it never really settled on those routes. The throughput never matched the packet generation rate due to all the wandering data packets that were being sent on exploratory links. The high queue routing exploration rates resulted in significantly higher router congestion, because we were sending more packets in random directions. Queue routing with the single radio nodes and the dual radio nodes experienced about the same throughput. That was the big surprise. And Warp 5 used to learn router forwarding information to avoid router congestion altogether and just solve the problem. Conclusions. Queue routing and shortest path protocols do not minimize router congestion in high offered load situations. In fact, with all those wandering data packets, queue routing actually makes the problem worse. Warp 5 learning algorithms effectively mitigate router congestion in wireless analog networks. Feedback in terms of total router load is not always effective in mitigating router congestion. This is what we've seen in the little 6-node network example. Router congestion is better mitigated by the request and reply packet propagation than with queue routing, trial and error, stumbling around trying to find the routes. We did some experiments with noise. This is a topology we used. There are 3 noise sources. There's a very powerful noise source in the center that's going to destroy a lot of packets even at a very slow and very resilient rate, and we have some smaller noise sources that are going to cause some packet losses. In this example, we have a poor selection of routes. 4 of the routes are just too close to that noise source, and we're going to lose a lot of packets. But honestly, I'm happy with that picture. That's picture wrong. Establish routes in a noisy environment. Again, nodes have identical routing, queue size, forwarding capacity because they're heterogeneous. I am setting up 6 routes left to right. I want the top right, top left node, top right node. There's 6 horizontal routes right across. 2 initial or fixed transmission traits. I went to the extremes. I wanted the fastest and most susceptible rates, 802.11g, 54 megabits per second. I wanted the slowest and the most resilient rate at 6 megabits per second. The noise sources were on all the time. They were on from time 0 in the simulation. And either route is very fast, so I can move all of the routes through any node if I want to, and we don't have a congestion problem with congested nodes. Strong noise source at the center and weaker noise sources at the corners, as we've seen. The experimental results, again, we were trying to push packets to, in this case, total demand would total off the load would be 200 packets per second. We would have a line about here. AODV with 1 radio and 2 radios. Slightly weird result, ultimately reasonable, in that the single radio throughput was actually higher than the dual radio throughput. That is not reflect on single versus dual radio. It was just when node 7 wants to talk to node 8, node 21 wants to talk to node 22, just as a random fluke, just randomly, AODV chose the routes that went down from node 9 up through node 15 and near the noise source. It just happened to send 3 of the routes near the large noise source. Randomly, again, as a random result, the single radio it sent 2 of the routes near the large noise source. So I'm not indicting AODV here because of 1 radio and 2 radio. It's just how the simulation turned out. With Q routing, we did experiments again at the most susceptible, at the least susceptible rate. This is also 6 megabits per second. High and low exploration rates. Q routing never caught on about the noise source. It was unable to learn. So what it did, it just kept sending packets in all sorts of random directions, and most of them got through. It did better than AODV did in a consistent fashion, in a more or less consistent fashion, but it just used all the routes and it never learned.
What's the difference between the second graph, top second box?
Oh, here. I also ran simulations at 54 megabits per second, very susceptible to noise, and I got, barely any 67%. I did similar things here for AODV and got, it's not on this plot, barely along here. And what happened with AODV was it couldn't even build all 6 routes.
So changing the percent of exploratory packets didn't really change?
It didn't really change. High and low, all did about the same. We weren't looking, again, because we made the router so fast, router congestion wasn't a problem. We just had this kind of meandering around, and it leveled off around here. And that reflects just sending the packets along and ignoring noise. The top pictures, again, I'm just carrying these over from the previous slides. This is Q routing again, identical slide, identical topology. We're looking for 200 packets per second. AODV managed that. We did 2 sets of discoveries, 1 at 4 seconds, 1 at 0 seconds, 1 at 4 seconds. Warp 5 caught on, figured out the routes, learned to avoid noise, and got its throughput to pretty much match generated packet rate. And you can see the topology has learned from that noise, and it's avoiding those noise sources as much as it can. It can't avoid noise altogether because there is no route. It's not going to get near some noise source. Established routes in a noisy environment. Like we saw, Q routing never found stable routes. It didn't learn from noise, so throughput never matched the packet generation rate. It could not adjust the transmission rate in for the very low 54 megabits transmission rate. Again, Warp 5 had the ability to say, oh, 54 megabits wasn't working. Go back to the previous slide. It doesn't. In fact, I start with 54 megabits as well, and it just adjusts the transmission rate upwards. Downwards, something more resilient. High-end, let's see, Q routing could not adjust the transmission rate. High and low Q routing exploration rate did not result in significantly different throughput. The graphs all look the same, about the same for Q routing. Warp 5 built all 6 routes, and the packet arrival rate is 100% of the packet generation rate. It adjusted routes without rediscovery after experience with noise. And so because Warp 5 was using what it learned at the map level, moving that and using that information to influence what was going on upwards at the network level, it made different forwarding decisions in response to noise. When a particular neighbor showed that it was particularly noisy, Warp 5 simply shifted over to a different neighbor. Let's see, all right, so Q routing and short path protocols don't manage noise. The Warp 5 learning algorithms do manage noise successfully. In cross-layer learning allows Warp 5 to make different packet forwarding decisions without error packets or rediscovery. So this shows that it's better to treat inevitable packet loss as a learning opportunity rather than a cause for error or rediscovery. Since packet loss is inevitable, let's learn from it. Get the lesson from this. Some observations. Novel aspects of OR5 protocol. It factors the effects of noise as well as congestion into routing and packet forwarding decisions. Concept learning mechanisms select the most efficient MAC level transmission rate using a modified k-on banded algorithm. Yeah, folks, we'll talk about what's a record respond to the k-on banded algorithm. It combines information from the MAC layer and contention or congestion information from the network layer into routing decisions. The ability to make different forwarding decisions is in response to noise without rediscovery. This is a sort of a classic AI algorithm. When I talk about k-on banded, there's the idea, I guess they got this from Las Vegas, they had a slot machine in Atlantic City. They call that the one-on banded. In the k-on banded problem, you have either k different slot machines or you have one slot machine with k different arms. The goal is to find which arm gives you the greatest payoff. Each arm gives you a different payoff, but you don't know what the payoff of each arm is beforehand. So you have to experiment. So, all right, I'll try this arm. Although that's giving me this payoff, I can try this arm gives me this payoff. What you're learning during that, you're saying, well, this arm gives me a better payoff than that arm. But this arm over here that I haven't tried yet might be even better. So how do I get the maximum payoff? How do I get the maximum number of coins out of that slot machine? Do I stay with the one that I know based on previous experience gives me the best one, or do I try to find an even better alternative? How much time do I spend with what I know? How much time do I spend exploring what might be a better alternative? That is the k-on banded problem. They have wonderful theoretical problems. Nobody's built a multi-arm slot machine to my knowledge. This is what the AI folks like to do. Observation. If we go back a few slides, even when OR5 was doing the job in the noisy environment, there was still some sort of variability there. It was not nice and flat. These are random and transient asymmetries between the data packet arrival rate and the forwarding rate. These occur when the data packet arrival rate is high in an environment where there's a lot of contention. This is the 802.11 distributed, what is that? The 802.11 DCF, which is doing the random backoffs, and every once in a while you get a really large random backoff, distributed control function. You get a really large random backoff, that node just sits there waiting and counting and waiting and counting, and its countdown is slowed because there are so many other packets in the environment. We experience these sort of transient dips in throughput. This is because of the 802.11 distributed coordination function. An extra benefit, the noise component of the OR5 routing metric also measures contention for the communication channel. And it actually should result in less contention, and that results in less overlap of the routes and less jitter. Future work, talking about link failure, mobile ad hoc networks, and quality of service. I have lots to say about that. Detecting link failure, let's go back. Noise is always present in the environment. Standard definitions of link failure, especially for wired networks, are arbitrary and a learning mechanism. So trying to do that, trying to impose an arbitrary definition of link failure based on different application requirements seems kind of silly. You can move video and you can lose a certain percentage of packets and still have an acceptable video image. However, if you're moving audio information, you can lose far fewer packets before you get an unintelligible audio channel. Does that make sense? Okay. So trying to define it in terms of the protocol itself rather than the application seems kind of silly. So the content definition has to be application specific. Global ad hoc networks. One question is, how mobile can nodes be? We talk about nodes moving around and still trying to maintain links and paths to the network. Well, how quickly can you build paths, and how quickly can the nodes move before you can even build paths to keep up? At some point, these things just start to stir around. Where are the thresholds? A little bit about the random waypoint model. Usually, a lot of protocols are evaluated in terms of the random waypoint model. It's not diagnostic. It's evaluative. It gives you some information. It says, oh, this protocol has done this well. You compare protocol A to protocol B, and you get a sort of one number for protocol A and another number for protocol B. It's evaluative. You can compare A to B in that sense, but it does not tell you where is a particular protocol failing to keep up. Why is one protocol inferior to another? Quality of service. If you want to describe, not in terms of time, but in terms of power consumption, variance, and so on, those are issues that also need to be addressed. So I'm trying to include this. So what we've introduced here and discussed today is a new cross-layer routing metric that reduces noise and congestion to time. It uses recent experience to make routing and forwarding decisions. We've also got a new cross-layer wireless routing protocol, or 5, that uses the routing metric and other machine learning mechanisms to establish new routes and adjust existing routes as needed to manage congestion and noise in wireless ad hoc networks. Our conclusion here is that noise and router congestion affect wireless ad hoc networks. Nothing new to anyone here, of course. Queue routing and shortest path routing protocols, queue routing being a machine learning protocol, does not manage noise. A cross-layer routing metric is feasible using time and information layers to manage noise and network congestion. This cross-layer routing protocol has been applied to 5, it manages noise and congestion, and the experiments demonstrate the feasibility and usefulness of machine learning in managing noise and router congestion. At this point, I'll stop, I'll breathe. I will now entertain questions